Hi all. In the last class we have seen how to uh, relate the coordinates of a particular vector v relative to two distinct bases, and we have seen that the coordinate of v relative to the basis d can be written as matrix times p times this matrix is denoted by cd pcd times the coordinate of v relative to c, and we call this matrix as transition matrix. Okay, so this matrix is what we called the transition matrix. So this will transform the coordinates of v relative to c to the d. So from c to d, this is the justification of the notation. So this matrix will change the coordinate of a particular vector v relative to c to the basis d. Okay, now we will in this class we will discuss the so please note this definition, transition matrix. So define transition matrix means you define this, we have two ordered bases c and d, then any vector v belongs to v can be expressed as in this form. So then this matrix is what we call the then matrix is defined as the transition matrix. Okay, once you write this transition matrix, then we can state theorem 2. In theorem 2 we will prove that this matrix is invertible and it has an inverse matrix. This is the second theorem, the transition matrix from C to D, and that is denoted by PCD, where both C and D are the basis for the same finite dimensional vector space, is invertible. So this matrix is invertible, and its inverse is the transition matrix from D to C. Okay, that means if you write this matrix P C to D, so this is the matrix obtained from the equation from this is obtained from this equation. V D can be written as P times C D times V C. Okay, and we have another transition matrix from D to C as well. Okay, because this is true for any C and D, we can get this matrix. So this is from the equation. This transform the coordinates of vector relative to D to C. Okay, so that will give from the equation VC is equal to P, this is D to C. Okay, so these are the two matrices time this times D. Okay, so we will prove that the product of these two matrices are the identity matrix. Okay, because we need to prove that this matrix PCD is an invertible matrix. In order to prove this, we define the product of these two, PCD and this PDC. Suppose this is a matrix A, and entries of this A is obtained, or we named and elements of this entries of this A as A11 etc. A1n etc. etc. an1 etc. ann. Okay, we will prove that this is the identity matrix. Okay, so this is because if we write this V D is equal to by definition this is VD is equal to P C D times this VC. But we know that what is this VC? VC can be written as by replacing this VC by this expression PDC times VD. We write this is PCD, and we replace this VC by this equation, that is PDC times again we have VD. Okay, so we have this expression. So this can be written as A times, we have put this A is equal to this matrix, this product. So this is A times the coordinates of V relative to the basis D. Okay, now compare this equation, VD is equal to this time. So when you put this is to any particular vector V, so if we put first V is equal to the coordinate matrix the vector 1 0 0 etc 0, so this is the vector in V, and we call that, and we put this is equal to Vd, then that implies this equation will implies 1 0 0 0 0 0 etc 0 is equal to, from this you can write a times a is a11 etc a1n, a21 etc a2n etc an1 etc ann. So this times the vector vd, again the coordinate of this is our vd, so we write this is equal to vd, so vd is equal to 1 0 0, then this the vd is same as 1 0 0 0. So these are the vector or the scalar corresponding to that one, and this is when you take the product of this, you can get this is equal to a11, and from the second row we have a21 etc an1. So this will be the equation. That means this a11 is equal to 0 and rest of them are a1 is equal to 1 and rest of them are 0. Okay, so from this you can write a11 is equal to 1 and all other quantities in this column matrix is 0, a21 etc an1 is equal to 0. Okay, when you put this vd is equal to 0 1 0 0, that means if you choose the vector whose coordinate is 0 0 0 1 0 0 etc, then that will become, that equation will become 0 1 etc 0, that is equal to this matrix, the same matrix times 0 1 0 0 0 etc. So when you multiply that, we can get the second entries in the second column. So a 1 2 etc etc a n2. So this will give the next set of coefficients, that is a12 equal to 0, a22 is equal to 1 and all others are 0, etc an2 is equal to 0. So when you put in this manner, we can get all the entries a11 equal to a22 is equal to etc ann is equal to 1 for a, and all other aij equal to 0 for I not equal to j. So this gives the matrix A is identity matrix. So the matrix A is nothing but P, the matrix P relative to C D, and times the matrix P related to DC. It shows that this matrix is invertible with inverse this PDC. So which this proves theorem 2 as well. Next we will discuss this problem. Find transition matrix between the two bases G consisting of the vectors t plus 1 and t minus 1. These are the polynomials, and H consisting of 2t plus 1 3t plus 1. These are two bases for P1. P1 is the set of all polynomials of degree at most 1. Okay, so setting V is equal to, if we write V is equal to 3t plus 5, then you write this is equal to 4 times t plus 1 plus minus 1 times t minus 1. When you write this, then you can get this 3t plus 5, and we write this, the same 3t plus 5 can be expressed as 12 times 2t plus 1 plus minus 7 times 3t plus 1. Okay. So these are the two different expressions for 3t plus 5 with respect to bases G and H. Okay, so from this you can write the coordinate of V relative to G is equal to that is obtained from this expression. So these are the scalars, so 4 minus 1, and from the other expression you can get the coordinates of V relative to H, so that gives 12 and minus 7. So these are the two different coordinates for V corresponding to these two different bases, and finally we will verify that what is the relation between these two. So now we will prove how do you get this transition matrix? In order to get the transition matrix, we need to write, in order to get the matrix P, we write this is the matrix P, write it as P corresponding to this CD, sorry, GH. Here we have GH. Okay. To get this matrix, we need to first of all we write the matrix HG first, then we will find GH. So it is easy to first you find one of these matrices and then you take the inverse of that, then you will get the other matrix. So first we write P H G. So in order to get this matrix, we need to write the elements of this H as a linear combination of G. That means we write 2t plus 1 is equal to 1 by 2 times t plus 1 plus, sorry, 3 by 2 times 3 plus t plus 1 plus 1 by 2 times t minus 1. When you add this, you can get this 2t plus 1, because the when you expand this, you can get 3 by 2 t. Here from this, the second expression, we can get half t. 3 by 2 t plus half t, that will be 2t, and this is 3 by 2 minus half, that is equal to 1. So from this expression you can write the coordinate of this 2t plus 1. We call this is equal to u1. If we write this is equal to we write this is v1, and this is our v1, this is our v2, and this is our u1, and this is our u2. So v1 can be written as a linear combination of u1 and u2. So this will give the coordinates of this 2t plus 1 relative to the basis u. Okay, the basis g. Okay, so here we have g here, and this consisting of the scalars 3 by 2 and 1 by 2. Okay, in the similar fashion, you can write this v2. What is v2 here? v2 is 3t plus 1. Okay, so this can be written as 2 times t plus 1 plus 1 times this t minus 1. So that will give this one, 2t plus t, that is 3t, and 2 minus 1 is equal to 1. From this you can write the coordinate of this v2 relative to the basis g. This is relative to the basis g is nothing but 2 comma 1. Okay, so if you write this, then you can easily get the matrix P H G. That is nothing but this will constitute the first column, that is 3 by 2 1 by 2, that constitutes the first column, and this constitutes the second column 2 1. So this is the transition matrix PHG. So in order to get the matrix PGH, we need to write the inverse of this matrix. So we write PGH. How do you get this matrix? So that is nothing but the inverse of this matrix. So inverse of this matrix is obtained by this is nothing but the PHG inverse. So this is same as PHG inverse. Okay, so this is this matrix. So first of all, you find the inverse of this matrix. So then the determinant of this matrix will be 3 by 2 minus 2 times half, that is 1. So this is 1 by 2. This is the determinant. So 1 by determinant means, so this is 2 by 1. So we write 1 by determinant, that is equal to 2 by 1. And in order to get this is 1 by determinant A into adjoint A. In order to get the adjoint, you just interchange the diagonal entries. This is 1 3 by 2, and just change the sign of the off diagonal entries. So that is minus 2, that is minus 1 by 2. So this is the easiest way to write inverse of this or adjoint of 2 by 2 matrix. So this is nothing but, this is equal to, when you multiply it with 2, then the first entry will be 2 and second entry will be minus 4, and this entry will be minus 1 and this will be 3. So this will give you that matrix PHG. Okay, from this PHG you can write PGH as well. So now we can verify these things. So when you multiply this, we can verify that PHG is equal to times this VH. Okay, so what is this one? PHG. What is PHG? This matrix 3 by 2, 2, 1 by 2, 1 times this VH. VH is this one, coordinate of V relative to H, that is 12 minus 7. So when you multiply this, you can get a column matrix that consisting of the entries. The first entry will be 3 by 2 times 12, that is 6 times 3, that is 18, and we have 18 here. This is not 18, that is 3 by 2 times 12, that is 18, that is 3 by 2 times this 12, and minus 14. Okay, we have 2 times minus 7, that is minus 14. The second entry will be 1 by 2 times 12, that is 6, and minus this 1 times this minus 7, so that will be 7. So this will give this is nothing but 4 the column matrix 4 comma minus 1, and this is, here we have written that this is VG, so we can write this is equal to VG. So we already discussed what is this, or we found that this PHG is equal to this matrix, and from this you can write the inverse as PGH, and we will shown that, or we will verify that for this particular VG and VH, P times this will give this VG. Okay, so this proves the problem what we have stated above. And in the next class we will discuss the remaining part of this section, change of basis. In that we will discuss that what is the relation between two matrices, two matrix representations corresponding to a particular linear transmission. That means if A and B are two representations of the same linear transmission, then how do you connect or relate these two matrices of the given linear transmission? So that we will discuss in the next class.